Okay, good afternoon, everyone. Can you hear me loud and clear? All right, thank you. Okay, so let's wait for 2 more minutes, then we can start the class. Okay, I think we can start the class now. Okay, so let me stop sharing the QR code here. All right, so okay, before we start, I have a few questions for you. First of all, how was the test? How was the test? Was it easy? Was it hard? Was it long? Was it short? Anyone? Okay, okay. So I don't know what is okay. uh, right. So I haven't marked the paper yet. For question one is my question. So whoever set the question will mark the question. So question one is my question. So I have about 400 papers to mark. But you know, last week is Hari Raya kan, so didn't do anything. Cannot do anything actually. So still yesterday ada open house lagi, and then so it's really hard to start marking. But I'll start it later lah. So question number one and question number two. Question number two is trust element. So that's one question. The second question is, do you think that assignment 5, which is test 1 review, helpful or not helpful? Anyone? Okay, Dalila said it's very helpful. Okay, so if the review is very helpful, what I'll do next is I have another review for test 2 and another review for your final. So this is what I'm going to do. So the last class before test 2 or the last class before final, I'll set I'll give you a review assignment. Okay. But the thing is, you must do the review. You must do, because I give it as a bonus assignment, kan? So you have to do it lah. I'm trying to help you. That is one of the reasons. I'm trying to help you to get good grades for your test, and also I'm trying to help you in your assignment punya marks lah. Bonus. It's a bonus assignment. All right. So okay. So that is done. So from now on, before we have any test or any final exam, I'll do the review. All right, so let's look at where we are so far. Where we are so far in terms of our classes. I think I think we are behind by 2 weeks. So never mind, we have to catch up lah. Whatever it is, we need to catch up with the our schedule, with our schedule. Uh, okay, so this is our e-learning portal, e-learning portal, and today is the 8th of May, 8th of May, which is this one, So this is the topics that we are going to discuss, basically our CST elements, CST elements. And okay, I'm supposed to let you know about this, but I think I forgot. So because we'll be having our project, our group project, So what you need to do is to find your partners. Okay, I'm not sure. Maybe we do it in a group of 3. Okay, for the project, a group of 3. So when you pick your team members, please make sure, first of all, that he or she is not dropping the class. Okay, let's say you have 3 members and suddenly one of your team member decide to drop the class because score dia tak bagus. Test one day is not very good. Then he said, okay, no, I'm going to drop the class. So you are left with only 2 group members. So please, that's one thing. The other thing is, please, when you pick a member, make sure that your member will participate. Okay, I have cases last semesters where this student join a group because dia just want the group project marks. Dia tak buat assignment, test dia pun tak lulus, and then dia join a group yang budak-budak bagus. And then budak-budak bagus ni complain lah. Doktor, dia ni tak buat kerja apa-apa. So which is not good. So when you pick your members, please please make sure that they will participate. Okay, janganlah ambil orang yang performance ni tak bagus. Okay, then you might be having a problem nanti later on. Because biasalah, this is every year, every semester sama je. Ada this kind of cases. Okay, so I leave it to you about this. Selalunya, if the class is face to face, I'll do the selection. But because of online ni, I'll leave it to you to choose your own members. A group of 3, a group of 3. So this, remember, I think earlier this semester I mentioned about you downloading the ANSYS software. So this is the idea here. So you can download the ANSYS software here. Let me make it a little bit bigger so that you can see. Okay, so download the software here. This is the link. And then there are also some tutorial, free online tutorial. And then I also have my tutorial here, ANSYS Beam Element Demo and solving frame problem using ANSYS. Okay, this is my video lah. You can watch the video. Okay, so please, this one is for the project because our project will be using software. Our project will be using software. So you need to be using ANSYS. Okay, I recommend that all of you, all the team members, download and use the software. This is just for familiarization. Familiarization. Okay. So I forgot to tell you about this during the break. And I think we missed this one. I think we are at this point actually, but we should be at this point. We are at this point, beam elements, but we should be here at CST elements. Okay, so we are kind of behind lah. We are kind of behind. So of course, this one is the lecture is by Dr. Nick, Dr. Nick Ahmad, Dr. Nick Ahmad Ridwan, Aero, from Aero. So I told him that can I just use your link to copy? Dia boleh. But I have my own video for this, the derivation. So basically, assignment number 6, which is this one here. Let me show you. Let me share this. Assignment number 6 is basically the derivation, beam element derivation. So what you can do here is you watch the video and at the same time look at your question, because the answer to this assignment 6 question is in the video. Okay, so my recommendation is to do it while watching the video. Okay, so do assignment 6 while watching the video. So that's the best part lah. So it will make your assignment easier. So the whole idea about this question, assignment 6, is for you to understand the derivation, because this is a slightly different kind of the nature of the problem is kind of different from the beam element. Sorry, not the beam element, the bar element and the truss element that we had done before. Okay, this is slightly different, different approach. Okay, but anyway, don't worry, because the video is there. So you can do this while watching the video. And at the end, we have this one, the application. So this is the problem. So the first part, from question 1 to 10, is basically it's not a question. Basically, it's just a steps. Step 1 until step 10 is in the video. You can follow through the video. And question 11 here is the application of what you have derived. Okay, application that what you have derived. So this is the one. This is the actual question. The rest are just derivation, a step-by-step derivation for you to understand what is a beam element. Okay, so that is assignment 6 lah, which is here, this one, which is this one here. Okay, I already put it on the website. You can just download this, and it is due 1 week from today. Today is the 7th. Today is the 8th of May, and a week from today is the 15th, before 12 noon. Okay, before 12 noon. All right, so this is the one. And the frame element is again from Dr. Nick. I have the assignment, but I have not put it on the website yet. Okay, I have it, but I do not put it yet. I think we need to do this quickly, because we need to catch up with this. I believe next Sunday is also another holiday, right? If I'm not mistaken, Hari Vesak. So we miss another lecture. We miss another lecture hours. All right, so what you need to do is after this class, please download the software. It's huge, It's huge, 1.8, I think 1.8 gigabyte. Please use Wi-Fi lah. Do not use your phone data. And then I have the demo of how to use ANSYS. Okay, for your information, I'm not an ANSYS user. I am an Abacus user. Okay, but Abacus has its own problem. In this case, for Abacus Student Edition, even though it is free, but it is limited to only 1,000 notes. 1,000 notes is too small for you to do anything. But for ANSYS Student Edition, it is up to, I believe, 100,000 notes, which is, I think, good enough for our project. So, I'll switch to ANSYS because of this. So I'm not an ANSYS user. You might want to find a better tutorial somewhere. Okay, my tutorial is very basics. Basically, if you know how to use ANSYS, if you know how to use Abacus, you should be able to use ANSYS. But there are some features that I might not be familiar with. For example, when you are learning how to drive a car, you might use Kancil or Viva, right? But when you have the money, you buy a better car than a Viva. So a better car, of course, has a lot more features, which is not in Viva. The same thing with this thing. Okay, so you need to adapt. So I did some demo for beam element. So I think this one is the same problem as this one. But this one is using ANSYS. You do your calculation manually using the formula that we learned, and you can also double check your answers using the ANSYS, which is this one, which I saw in the video. Okay, the same thing with the frame element, the frame problem. So this is just to make sure that we know that what we are doing here is implemented in a commercial software, Abacus ke, ANSYS ke, they are using the same theory, what we are learning. So why we are doing it manually? Because we need to understand. Okay, because when you are using software, normally people treat software as a black box. What coming in will go out. So if you put in garbage, garbage will also go out. So the whole idea is here is to understand, to understand the software, to understand the theory, so that you will not put in garbage. All right, so this is the assignment. This is the assignment. So again, just do it while you are watching the video. It will be very helpful. All right, so we need to catch up. We need to catch up. And again, sorry about the the project. 3 members per group. 3 members per group. 3 members per group. Again, I caution you about selecting the proper team members. The proper team members. So make sure that the team members do not have the team members.
Halo, halo.
Yes.
Eh,
Wrong room. Please go somewhere else. All right, so what we have here is that 3 members, 3 team members, and make sure that your team member is not planning to drop the class. The second thing is make sure your team member is not a parasite. I hope you know what I mean by parasite. He's taking all the grade but not doing anything, not willing to participate in your the work. So this is again another issue. So be very careful. Be very careful about this. All right, so that's it for my announcement. So what I'm going to do today is to talk about assignment number 6. Assignment number 6. So before we go for assignment number 6, let's review what we have done so far. What we have done so far, I think because I forgot when was the last time we have this live session. It was very long time ago, I guess. All right, so remember the first thing that we learned is bar element. Bar element. That's the first thing. And the bar element has only 1 degrees of freedom per node, right? So we have Q1, again Q2, uh, Q1, let's say this is node 1, this is node 2, and we have Q1, and we have Q. So what we have here is just A, 1 degrees of freedom, 1D element, which is bar element, and only 1 degrees of freedom per node. Okay, in this case, it's just the displacement of node 2 and or node 1. And I think this is on your test, right? This is on your test 1, which is my question, a very straightforward question actually. So if you do the review, you should be able to do my test question because I think it is very, very similar to the review session. All right, so that's bar element. And then the next thing that we did was basically we have a bar element. So let's say this is our x bar, which is our local coordinate, which is at an angle to our global coordinate system. And this is our angle theta. Okay, and this is node 1. This is node 2. So what we have here is that we have uh, two things here. We have Q2 prime, which is in the local coordinate system, and we also have Q1 prime, which is in the local coordinate system. And then, because we are interested in the global coordinate system, what we have here is we have for node 1, we have Q1 and Q2 without the dash, without the prime, which means that this is a global using global coordinate system. And for node 1, and we have Q3 and Q4 for node number 2. Okay, so now what we have is basically at each node we have 2 degrees of freedom. So we move from 1 degrees of freedom per node, and then when we tilt our, we put the bar element at an angle with respect to our global coordinate system, then we have 2 degrees of freedom. We have displacement in the x direction and displacement in the y direction, right? So this is how we move. And note that 2 degrees of freedom. And remember, I think in question number 2, you have this kind of question. Okay, you have this kind of question. And I mentioned that the most important thing is to keep track of your angle, how you measure the angle. If you screw up your angle, then your answer will be screw up also. Okay, that's the issue. Now, the next thing is what we want to do is beam element. So this is bar element. So thrust element. The next one was thrust element. What is a thrust element? Thrust element is basically a bar element at an angle, right? That's it, at an angle. Now what we have is a beam element. So what is the difference between bar, truss, and beam element? What kind of deformation that we have in beam element? For bar element, what we have is only displacement, right? Displacement. Also, the same thing with truss element. So if bar element is either vertical or horizontal, then we have only in one direction. But for truss element, when we put it at a certain angle, then we have Q1, Q2, Q3, and Q4. Basically, our displacement in the horizontal and the vertical direction. So basically, bar and truss are just displacement. Okay, deformation is just displacement. What about beam element? What kind of deformation do we have in beam? Okay, what kind of deformation do we have in beam? What do you remember about beam? Formula. Do we have stress in beam? What is the stress in beam? What's the formula for stress in beam? Anyone? 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 Can somebody answer my question, please? Banyak sangat makan kuih raya ke? Dah lupa dah semua. So for bar element, we know that our sigma is just, right? Or sigma is just E epsilon, right? Where epsilon is just our delta V or dV dt. Sorry, d dV dx, right? So this is the strain and this is the stress. Sorry, this is for bar and bar element, bar element. So what about for beam element? What kind of deformation or what kind of quantity that we have here? So of course, when you do, you have sigma equal to MC, not MC. Uh, 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 MC or My over I, right? This is one of the stress, beam bending stress. So what's the other one? Any other thing? And what is the formula for strain then? Do we have strain in beam? We have stress, of course, we will have strain. So this is the relation. So in this case, our strain is just sigma over E, or for beam, then it becomes M E I Y. M E I Y. Okay, sigma is M Y over I, M Y over I divided by E. So this is our strain. Okay, do we have displacement for beam? Do you have displacement for beam? Oh, too quiet. Uh, oh, somebody said yes. Okay. I prefer that you use your microphone, because now it's too quiet. My room is too quiet. My floor has nobody except me. Okay. Uh, so this is too quiet. It's not. There's no motivation for me to speak. Actually, there's no motivation for me to teach because it's just like me talking to the screen, to my monitor. So that's why I need you to say something. So I know that. Uh, I know that you are actively listening to my lecture. Okay, what happened to my class before this? This morning, when the session ended, I didn't log out. I just stay there and watch how many of the students have not left yet. There are, I think, few students who left maybe after 15 or 20 minutes after the class ended, which shows that maybe that he's not in the front. He's not watching at all the live session. He just turned it on and went somewhere else. This is another issue, because you are not turning on your camera, so I do not know if you are in front of the monitor. All right, so this is another issue. This is another issue. So please say something. All right, so let's look at the question paper. Let's look at the question paper here. So, so this is our beam. This is our typical beam. So this is simply supported beam. And take note that these are the loads. So we have distributed load, we have concentrated load, and we also have concentrated moment. Concentrated moment, okay, uh, for beam. These are the typical loads for our beam. Note that in this case, if you read the textbook, it says that this shows that the direction is positive. The direction of the loading is positive. Note that positive here for the uh, moment is counter-clockwise direction. Counter-clockwise direction. Okay, so the resulting deformation. So for a beam, type of loading and resulting deformation are shown in figure 1. These loading are distributed load, uh, P per unit length over length L, and point load PM at point M, and concentrated moment MK at point K. So the resulting deformation of the beam neutral axis are the vertical displacement. Note that due to the load, load is positive when it is going upwards. So the beam deform. This is the shape before the deformation, and this is the shape after deformation. Note that this is your neutral axis. This is the neutral axis of the beam. Neutral axis of the beam. So this is the neutral axis of the beam for this unloaded before deformation, and this is after deformation, the neutral axis of the beam. So note that at any point, in this case at x, we have what we call a vertical displacement. So this is our position before deformation, and then initially it was at this point, and after it was loaded with loads, then it deformed. Basically, this point, the neutral axis move from this point to this point here. So this is what we call the vertical displacement. It is displaced by the value v. So this is what we call the v. And note that initially the angle or the rotation of the neutral axis before deformation is this line here, which means it has no rotation at all, or the angle is 0. But after deformation, see that at this point here, the neutral axis is at an angle here. Here. So now it has this slope, slope or rotation. So we know that there's an angle here. So there's an angle, or because this is the slope, we can say this is just, the slope is just your delta y over delta x. So the slope is just your dv dt. Sorry, dv dx. Okay, the vertical displacement with respect to the location of that point there, dv dx. So this is uh, the slope at this point here. Okay, just like your dy dx, just like your dy dx. So why do we need this here? Why do we need here? Because at this point, we know there's a moment and there's also a vertical displacement. So there are two types of deformation here. So we have rotation and we have vertical displacement. So rotation in this case is dv dx, or we just say v prime, v prime, v prime. So rotation here. So basically, if we know the slope here, we can also find the angle here. So this is the angle, rotation. So this is why we say this is V prime. This is the rotation of the beam. Initially, it was flat, and then after it was loaded, then it has this angle. Basically, it rotates this way. It rotates, okay? It rotates. So this is why we have an angle. So V prime is the rotation. So these are the two degrees of freedom in our beam element. Okay, remember that for bar element in neutral axis or is local coordinate system, or in neutral coordinate system or is local coordinate system, then what we have is just displacement. But for beam, okay, sorry, for thrust, we have displacement, again, displacement in the vertical and the horizontal direction, because the bar element is at an angle with respect to the global coordinate system. So in this case now, what we have is just a beam, which is at horizontal position, horizontal position, flat. And there are two kind of degrees of freedom. Deformation in this case, which is this one is the vertical displacement, and this one, which is this one, which is the rotation, which is the rotation. So in this case, slope, and this is what we call a rotation. So now, if we draw okay, so this is, if you read carefully, this is kind of your guidance. I put this as my, for you, for guidance. So we know that dv dx is just our rotation, but the rate of change of your rotation is what we call the curvature, and this is just simply d square v over dx square, which is this one, and this is what we call, sorry, this whole thing, the result of dv dx, d square v dx square is what we call the curvature. Curvature is basically the shape of the beam, like this. Okay, it's so this is the curvature. This is a curvature. Okay, it's a curvature. So the curvature is related uh, with this ME over I. So this is from beam theory, from your solid mechanics. I don't know, maybe solid mechanic 1, from your solid 1, solid 1. So uh, this is your curvature. And from this relation, we can find, we know that our moment is this. Note that E and I are, E is material constant, which is Young's modulus. I is basically, what is I? Anybody? What is I? I stand for Anyone? Anyone? Is anyone still on the screen listening to me?
Yeah, okay.
So what is I there?
Second moment of area.
Second moment of area. Ya ke? Alright,
Oh,
never mind. I'll let you check. Okay, so EI, because we know that m over EI is d square v dx square. So we know that this thing can be found from the geometry of the deformation. Okay, so we know that the moment is just EI times d square v dx square. So note that from our uh, analysis here, we know what is v prime, which is just dv dx. And once we know dv dx, we can find what is d square v dx square. And once we know what is d square v dx square, okay, so we can find the moment given that we know what is the material properties and also what is the I or the geometric properties of the beam. For example, if we are using I beam, of course, there's a table again, how to find the I for this kind of shape. This is the geometric part lah. So we also have C channel, for example, C channel, then we know what is the I, okay, and E and so on. So now, from this deformation, we can find our moment, our moment. Right, so let's go on and note that again, if you look at this, the deformation that we have for our beam, only two, rotation and our vertical displacement. And because of that, if we cut our beam to smaller pieces, because we want to do finite element, so we know that the degrees of freedom at the beam, so this is our element, this is node 1 and node 2, we know that we have the vertical displacement going upward as positive, which is Q1, and then we have rotation at node number 1, which is defined as Q2, second degrees of freedom for node number 1. And again, this direction counterclockwise is as positive. Counterclockwise is positive. Again, the same thing for node number 2. But the numbering, no, the numbering is similar to our truss element. In this case, odd is always for the vertical, and even is for the rotation. So note that this is just the vertical displacement at node number 1, and this is the dv1 dx. So instead of using this, we map it to q1, q2, q3, and q4. So this is the notation. This is the notation. So this is the degrees of freedom, and this is the deformation. This is vertical deformation, the vertical displacement at node number 1. This is the rotation at node number 1. Okay, noted by this prime. The same thing for node number 2 here. This is the vertical displacement, and this is the rotation. Okay, so we map it by using this. So this is just Q1, Q2, Q3, and Q4. All right, so how many degrees of freedom that we have for our beam element? We have 2 degrees of freedom for each node. Okay, and now it is not anymore just displacement. Okay, this is displacement and rotation. Okay, rotation. From the rotation, we can determine the moment. Okay, so we know what is the moment. Moment is just EI d square v dx square kan, which is this one lah, which is this one. And once we find m, can we find the stress? Remember that stress is just m I y. Okay, so once we find the moment, we can find our y. Note that in this case, okay, what we can get directly is v. V1, for example. But once we get V1 prime, which is equal to dV1 over dx, to find the moment we need to differentiate one more time. Remember this? See, we have to differentiate twice to get our M, yeah? So it requires a lot more work than bar element ataupun truss element lah. Truss element. So again, back to the bar problem. Remember that we know this is our Q2, this is our Q1, all right? Q2 and Q1. So this is node 1, this is node 2. So this is straightforward, right? And remember that I told you that in finite element, we can find the nodes, the displacement at only the nodes. What about at this location? Let's say this is our location, let's say alpha here. So how do we find Q or displacement at point alpha here? I think this is part of the test question, right? I think the test question asks you this. So how do we find alpha here? What do we need to find? What do we need to use to find the displacement at alpha, at the point alpha here?
Shape
Anyone?
function.
Shape function, right? Shape function. Remember that we said that shape function is our u, for example, is just n1 q1 plus n2 q2. And note that uh, we have 1 degrees of freedom at node number 1, and we have 1 degrees of freedom at node number 2. And this is the function, simple function. So we know that this is just 1 minus z over 2, which is n1, eh? And n2 is 1 plus z over 2. So this is the shape function here. This is the shape function. But now, take a look at this. My question here is, let's delete all this. Too crowded already. Okay. Okay, so now my question here is, uh, my question here is, what is the rotation? What is the rotation and the vertical displacement at, let's say, this point? Let's say beta. Huh. How do we find that displacement, vertical displacement and rotation at point beta? Anyone? So remember about interpolation. So I mentioned last time, a shape function is basically a interpolation function, right? Interpolate, because we know left end, we know one value on the left hand side, we know the other value on the right hand side. So what do? We just use interpolation function, which is in finite element we call it shape function. Okay, so in this case, again, we need to use a shape function, but this is the issue. Is it going to be n1 and n2 again, or is it need to be something else? Okay, so in this case, look at this. N1, N2 for bar element, right? And bar element has only 1 degrees of freedom per node. So only 1 for Q1, only 1 for Q2. But now, look at this bar element. Okay, the concept is still the same, but the application now is at a different kind of level, different kind of level, because before this, it is just for 1 degrees of freedom. But this is for 2 degrees of freedom, and we have 4 degrees of freedom. So in this case, what we need to do is that we need to find something, in this case, that the location, let's say beta here, it will have the term of Q1, Q2, Q3, and Q4, because Q1, Q2, Q3, and Q4 are all the known values, are all the known values that we have. Okay, so macam mana nak buat tu? Channel number 2. So we know that we need to use all the four values that we know, all the four values that we know. So in this case, what we need to do is we know that, for example, the V at this point, the vertical displacement at point beta is just V equal to shape function. So or basically this is V1, this is V prime 1, this is V2, and this is V2 prime. So we need all these terms here. So we know that it will be using, let's say this is V at point alpha, beta, it's going to use V1, V1 prime, V2, V2 prime. So again, what we need here is N1, sort of N1 and N2. But now it is not anymore only two or only two functions, but we have a lot of functions now. So N1 and N2 is the shape function. So N1 is one function, N2 is another function. So in this case, this is N1, one function. N2 is another function, only two functions. In this case, now we have four functions. For this kind of thing, note that we'll be using H1 plus H2 plus H3 plus H4. Okay, so now we have four shape functions that we need to use. The question now is what is H1, what is H2, what is H3, and what is H4? That is the question. And this is part of the question. This is part of the question. Note that we are using local coordinate. We are using local coordinate in term of z because our beam, again, our beam. So this is node 1, this is node 2. Okay, this is z equal to 0. This is z equal to -1. This is z equal to plus 1, right? So still, this is still a 1D element, but different degrees of freedom. So now the question is, what is H1, what is H2, and what is H3, and what is H4? So now I have given you the clue here. I've given you the clue. It must be this sort of function, third order polynomial, a third order polynomial, because we have four known values. If you remember from your numerical methods, okay, the degree of polynomial depends on the number of your known point. So for example, if you know 2 points, then your polynomial is order 1. So it is always less 1 than what you know. In this case, we have 4 known values, and the order of polynomial will be third order. Third order. Like this bar element, we know two values, okay, q1 and q2, and the order of the polynomial for the shape function is only 1, which is linear, kan? So in this case, this is linear, okay? But in this case, h1 until h4 is going to be a third order polynomial. So these are the requirement, okay? For vertical displacement, for h1, h1, vertical displacement at point 1 is 1. Vertical displacement at node 2 is also is 0, just like your n1. n1 is 1 at node 1, but n1 is 0 at node 2. The same thing here. And note, because h1 is for only vertical displacement, there's no slope. There's no slope because note that this one, h1, is just the displacement. There's no slope, there's no rotation. So the slope at node 1 is 0, the slope at node 2 is also 0. Note there are 4 boundaries condition here. One, uh, displacement is 0, 2, 3, 4. Note that now there are four unknowns and there are 4 conditions. Can we find what is H1? Of course, we can find what is H1. All right, so the same thing with V2. This is for V1, this is for V2. Note that for V2, again, this is just for the displacement. So the slope is always 0 for both node. But for V2, remember node 1 is always 0, but node 2 is always plus 1, just like our N1 and N2. But now look at this. This is V1 prime, and requirement is that the slope must be 1 at node 1. Okay, so this is slope 1. This is slope 1. And the slope at node number 2 must be 0, must be flat. And look at the displacement at node 1 and node 2 for V1 prime. Because V1 prime is a slope. It's not a displacement. So that is why the displacement here is 0 and the displacement is also 0. Again, this is V2 prime. Again, we have 4 boundary conditions, okay, to solve for H2. Okay, because it is in the form of A2, sorry, in this case A2, B2, C2, and D2. So we have 4 unknowns with 4 boundary conditions. Then we can find what is A, B, C, and D. Again, the same thing here. This is V2 prime, which is, again, there's no displacement. The slope is 0 here. Sorry, not the slope. The displacement is 0 here. The displacement is 0 here. But the slope at node 1 is 0. The slope at node number 2 should be 1. Okay, this is positive 1, because this is going upward. Okay, so these are the requirements. So if you derive it carefully, okay, you can get all these values lah. And I think it's in the textbook. It is in the textbook for H1 and H2, H3 and H4. It's either in the slides and it's also in the textbook. Okay, so I think time is up. So what I need to remind you is that you need to do this, you need to do this. There's a homework here. There's a homework which is this one here, beam element, beam element. So again, question 1 until 10 is just the derivation. It's in the video, it's in the textbook, okay. But 11, question 11 here is the application. Okay, take a look at the element stiffness matrix. It is a 2 degrees of freedom per node. Then we have 4 degrees of freedom per element. So the matrix is a 4 by 4 matrix. Okay, 4 by 4 matrix. And well, you know then, again, just like the truss element, right? Just like the truss element. Okay, so you need to show me this. Need to show me this. All right, so again, the derivation of your K matrix, K matrix. And again, this is based on your potential energy. Tak salah saya. Based on your potential energy. All right, so once you know what is your K, of course, you can find your K global. And again, once you find your K, just like our bar element, you can find your force vector. What kind of force do we have here? What kind of forces? We have 3 kinds. We have distributed load, we have concentrated load, and we have concentrated moment. Okay, so this is for distributed load. And okay, I didn't show how to get for the okay, point load and point moment is applied at the global matrix, at the global matrix, because it is not based on the element, it is based on the global matrix. And once you know what is the d square v dx square, you can find your m. Then once you know m, you can, because v is the shear force, then once you know m, you can find your m. And once you know m, you can find your, a soft copy of the textbook? No, I don't have a text, sir. I think you are smart enough to find the textbook. I think I told you the first day of class, you need a textbook. I told you you need a textbook. That I don't care how you get it, but you must have a copy of your textbook. Hard copy ke, soft copy ke, pinjam kawan ke, pinjam library ke, but you must have a copy because this is your source of reference. This is the source of reference. I think I gave to you during first day of class what we need. I think the list. I don't remember. I think this is the one. Let me open up. Uh, 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 this one. I think yes, this one here. I say here, textbook here. I told you during my lecture, I say, please have a textbook because this is your reference. The slide is not good enough because it is just a summary. It's just a summary. Sometimes it skip a lot of things. So you might have no clue or you be clueless on the jump. Too. So please read the textbook. And remember, I told you also about the textbook because I talked about this in the SLT lecture, student learning time and the Bloom taxonomy. Okay, so please find a textbook find a textbook, buy, pinjam kat library, pinjam kawan, pinjam senior, tak kisah, but you must have a textbook. Alright, so I think that's it for today's live session. Okay, until the next class, thank you very much everyone.
Thank you, Doctor.
Alright.
Gitu.
Thank you, Doctor.